Stuart Stubbs, product director at Quantum Science. I think you've joined us from the UK, right?
That's right, yeah. So my name is Stuart Stubbs. As mentioned, I'm product director at a company called Quantum Science Ltd, which is based in Daresbury Science Park, a prestigious science park in the UK, somewhere between Manchester and Liverpool. So we were founded in 2018, grown to about 20 people in that time, and we're a technology leader in producing nanomaterials with a world-class team and world-class facilities. So some of our wonderful quantum dot chemists working hard in our QD synthesis laboratory, and our device and film engineers working in our device laboratory. We have our registered trademarked INFIC best-in-class quantum dot infrared materials, and we have a broad pipeline of internationally leading companies as customers. So these are mainly sensor makers, some large material manufacturers supplying to the semiconductor industry.
Good.
Our intention is
jump in. Can you just click on hide? You see that little thing on your screen? Can you click on hide?
yes, sure.
That's it. Yep.
Yeah, so our intention is to disrupt this multi-billion US dollar SWIR sensing market with our strong IP, which is based on material synthesis, ligand exchange, and device. And yes, so I've had a good introduction already, but I just wanted to spend a minute on the SWIR imaging technology challenge. So obviously in shortwave infrared, we've got these really mature, very highly performing technologies like indium gallium arsenide and other 3 to 5 semiconductors. These have got really excellent sensitivity in the SWIR, very high performance. But the main problem with these is very low throughput. They're grown on indium phosphide wafers, small wafers, require expensive hybridization, complexity to fabrication, and that leads to a kind of high cost per sensor and also a limited resolution other than some really advanced technology. So quantum dot photodiodes aim to combine shortwave infrared detection with the CMOS ROIC technology. So silicon's really, really successful technology in the visible to the near infrared. And that's mostly because it's been very low cost, it can be very high throughput, can be done on large wafers, and those resolutions of our camera, our smartphone cameras is extremely high. But it's fundamentally limited. There's no absorption from silicon in the shortwave infrared, so that's its drawback. So quantum dot photodiodes, they can solve this sort of high cost, low throughput problem of SWIR photodetection by combining the quantum dot materials on top of the silicon CMOS ROIC technology, gain all the benefits of the silicon with the photosensitivity of the quantum dots out to the SWIR. So this low cost approach offers the potential for disrupting current applications, but also opening up new opportunities in new market areas. So just briefly look here, because SWIR's been introduced very nicely already, but we've got our silicon sensor limit around 1000 nanometers, which can be used for our visible camera sensors. We've got a very large number of high volume and mass market applications that need these shortwave infrared lights, this infrared wavelength. We can see that as we move through each wavelength, we're opening up more and more applications. And the nice thing about quantum dots is that we can tune their size all the way through these wavelengths just by tuning their size by just changing their bandgap. So we've got things like advanced consumer electronics, 3D mapping, augmented reality. We've got applications in automotive, so it can be in-cabin sensing of the driver. It can be gesture recognition, or it can be outside the cabin for LiDAR. It can be industrial automation or quality checks, such as checking the quality of foods, fruits, vegetables, checking drugs, seeing through certain plastics. We've got deep tissue imaging, so SWIR can penetrate into the skin more than shorter wavelengths of light can, and we can use for biometrics, fingerprint sensing, and so on. So what's Quantum Science's core strengths? What do we bring to this? So our synthesis capabilities of our quantum dot materials is the key pillar. We've got a lot of past experience in synthesizing different types of quantum dots, now focusing on the shortwave infrared wavelength range. The key sort of thing to point out here is we've got a world-leading size and shape homogeneity. So a lot of the times we use full width half max